Hello and welcome to my RenR 690 final project, assessing the reliability of LiDAR SLAM data in Costa Rica's tropical dry forest. So first we must ask ourselves, what is SLAM? So SLAM stands for Simultaneous Localization and Mapping. It's an emerging technology in forestry modeling and is typically used in mobile laser scanning. This takes less time to complete scans of entire plots than traditional methods and terrestrial laser scanning, and it could reduce existing errors and faults in the collection of tree metrics through LiDAR thanks to its mobility, which it would reduce occlusion and shadow effects. So my main objective for this project is to find an accurate way to extrapolate tree metrics using SLAM. And the tree metrics that we'll be assessing today are DBH, tree height, and stem numbers. And additionally, I'll be asking if the reliability of LiDAR SLAM changes with successional stages, species, or different tree sizes. So the two methods we'll be comparing today are the true method, which is traditional forest inventorying methods, including DBH tape, to measure the DBH, and a clinometer to find the angle, and then from there measure the tree height. And our test method is, as I've mentioned before, SLAM. This is what a SLAM LiDAR sensor looks like. It is multi-beam and can collect 1.4 million points per second in a point cloud of the forest. Here is what the data looked like when I input it into R. So we have your tree ID, the parcel, so the plot, the DBH measurements, the succession stage, the genus species, the tree height, and the stem numbers. Here are some descriptive statistics of the three measurements. Here, as we can see, DBH and stem number are both quite accurate with a very low difference mean. However, tree height has a difference mean of 9.04 meters and is consistently greater than the true value of the tree. And here are the distributions of these three metrics. As we can see there, the DBH and the stem number are both around 0, whereas we can see the data for the tree height being centered around 10 with not many outliers. And I wanted to further assess the reliability of DBH, so I split everything into successional stages in which they were located, and we can see that there is no difference, that the DBH measurements are pretty reliable regardless of successional stages. And then I took the 5 most common species in our plots and took a look at those DBHs, and once again they are generally quite reliable, with an outlier for Cochleospermum vitifolium and Sebastiana pavoniana, which have each have a difference of 10 centimeters and 9 centimeters at some point. And doing the same thing with tree height measurements now, we can see that there's, in the successional stages, that there is a difference of just under 4 meters between early succession difference and late succession difference. And then additionally, there seems to be another 4 to 5 meter difference between Cochleospermum vitifolium mean difference and Sebastiana pavoniana mean difference. And for stem number, we find that the LiDAR SLAM method is accurate in every aspect, whether it's succession stage or the species. And here are the box plots and distributions of our metrics by successional stage. So something very interesting here is for tree height in the box plot, you can see that the early IQR is greater than the intermediate or late. And you can also see the presence of outliers in the tree height difference for the early stage and the late stage, but not for the intermediate stage. And here are the box plots looking at the tree metrics for the 5 most common species in our plots. And here we have the distributions for the DBH and tree height of all 5 species. So here we can see again that tree height is very inaccurate, with constantly being overestimated by the LiDAR SLAM. Something else that's very interesting is Bursonoma crassifolia here is bimodal, which is worth keeping an eye out for. So since there is a wide range of trees and tree width in the forest, I wanted to see whether that had an effect on the accuracy of LiDAR SLAM. So here we have it split by true DBH measurement and their associated SLAM measurement. And here we can see that when there is a DBH greater than 40, that there is also a greater mean difference. And here it is shown to be minus 11 centimeters. And here are the histograms and box plots of these. And we can see here that on the bottom right that the skewness of the 40 plus category is due to 1 or 2 outliers where there's a difference of greater than minus 55 and minus 40. So what we learned so far from our analysis is that DBH is accurately calculated in LiDAR SLAM, and tree height measured through LiDAR SLAM is consistently overestimated by a mean of 9 meters, and this could be chalked up to a difference in methodology, and that LiDAR SLAM accurately counts and segments tree stems. In order to attempt to use tree height measurements, we could try to apply a bias correction because, as we can see here, there is a normal distribution. It just seems to be moved, shifted by 9 meters. So if I apply this bias correction of 9 meters, we can see that it is once again centered around 0, much like the DBH and stem values here for the box plot and for the histogram. And so this means that despite a few outliers, LiDAR SLAM is a generally reliable method to accurately measure DBH and stem number, regardless of successional stage, species, and tree size. This is also the case for tree height after a bias correction of 9.04 meters.